So last time, what did we do? I defined, right? I gave you definition that the integral from a to b of f of x dx was the limit as n goes to infinity of, the sum, let's say I equals 1 to n of f of x sub I star delta x, right? So, and I don't want to go through all the notation again, but this was our definition of the definite integral, right? This is the so-called Riemann integral. And I indicated to you last time, and we calculated some specific numerical examples, that this is trying to do what? This is calculates the area. Area bounded by y equals f of x for a less than or equal to x less than or equal to b. Well, I'm here to make a confession. That's not quite true. All right. This is only true, the statement I just wrote, this is true if f of x is greater than or equal to 0. All right? But if f of x is negative, all right, then this summation that we're looking at could be negative. Let me just kind of give you a picture. So if I had something like, the function looked like this, perhaps, right? And this was my y equals f of x. We are assuming that f of x is continuous for the moment being. There's no jumps in it, So in this case, the integral from a to b of f of x dx, it wouldn't be the area bounded between y equals f of x, right? It would be what we call the signed area. What's the signed area? Well, here it is. So if we say that this area is, let's say, like A1, and this is area A2, okay? Then if these are the areas of those respective regions, this integral is actually minus A1 plus A2. This is a signed area. So it counts area below the x-axis as negative, and it counts area above the x-axis as positive. Just to give you a specific example with a function that you know and perhaps love, we could look at like sine, right? Y equals sine x. And the integral from 0 to 2 pi of sine x dx, what would it be equal to? What do you guys think? What can you tell me about this this red area here, and this blue area over here? If I drew my graph right, they should be exactly the same shape, right? The one is just the other turned upside down, shifted over, right? Those two things have the same area, but one of them counts as negative. So what's this integral? Well, I'll tell you, it's 0. Because the positive area and the negative area cancel out if we go from 0 to 2 pi. All right, so and I have now fessed up, actually the Riemann integral doesn't just calculate area. For a function which is possibly negative, it calculates quote-unquote signed area. Does that make sense? Okay. Now, so now I should talk to you a little bit more about the properties of the Riemann integral, all right? And some of these properties I'm not going to prove. I'm just going to kind of say, it should be kind of geometrically obvious that these things are true, all right? Uh-oh. Can I erase?
No, that's fine.
Okay. It's okay? Okay. I got carried away with my erasing before I didn't double check with you guys. All right, so here's some properties. Properties of Riemann integral. I've forgotten how to spell Riemann all of a sudden. Properties of definite integral. There we go. I can spell definite, definitely. So if we had, here's one. If this was A, and this was C, and this was B, right? You guys tell me, what would the integral from A to C of f of x dx plus the integral from C to B of f of x dx be equal to? If A, C, and B are arranged as I have them here, you know? A less than C less than B. If you want the area from A to C plus the area from C to B, that's the same as what? The area of the whole thing. What's the area of the whole thing? Well, that's the integral from A to B, right? So this is the integral from A to B of f of x dx. This particular property is important when we integrate functions that are like piecewise defined, because we may need to like break the piecewise defined into pieces to do the integrals on the different pieces. We'll use that property there. Okay, something I don't want to draw a picture for, but it's just kind of obvious. If f of x is less than or equal to g of x for a less than or equal to x less than or equal to b, then guess what? The integral from a to b of f of x dx is less than or equal to the integral from a to b of g of x dx, right? Does that make, I mean, I think that makes a lot of intuitive sense, right? If the one is always bigger than the other, then it certainly bounds a larger area, right? But this theorem still makes sense when f and g are negative. So that's another property. I should make a remark. I keep forgetting. But if we had the integral from b to a of f of x dx, that's by definition minus the integral from a to b. So if you we do allow for the bounds to get, so like we've been assuming a is less than b. If you had something like integral from 7 to 2 of f of x dx, what that means is minus the integral from 2 to 7 f of x dx, which we've described how to set up the integral from 2 to 7 in terms of, chopping it up into boxes and taking the limit. But the integral from 7 to 2, that's a weirdity that I'm just telling you, this is how we define it, with a minus like that. What are other properties of the definite integral? How about this? If we had a function, right, and it was stuck between little m and big M, right? Suppose the graph of a function it's bounded between little m and big M, right? From A to B. So we have, little m less than or equal to f of x less than or equal to big M. Bounded above by big M, bounded below by little m. Well, check this out. If you look at the area, you guys tell me, what is the area of the rectangle that I'm about to graph? You guys tell me, what is the area of this rectangle right here? Can you tell me, what's the area of that rectangle? Length times width, right? What's the length? M, maybe M is either the length or the width. I mean, whatever it is, right? M is one of the distances, little m. What's the other distance from here to here? We do what? We do B minus A, right? That gives me the distance. Like if this was 7 and that was 3, 7 minus 3 gives me 4. 4 is the distance. So that's that area, right? And I'm going to ruin my picture by doing this, but you'll forgive me. What if I made this big rectangle like this, right? See what I'm saying? That big rectangle. What's the area of that? It's the height of it is big M. The length is still B minus A, right? How is the integral of the function which is bounded related then? So what I'm saying is this actually tells you that the integral from A to B of m dx is less than or equal to the integral from A to B of f of x dx, right? Is less than or equal to the integral of big M from A to B dx. But we just explained that m, the integral, the little integral, is little m times b minus a, right? So there you go. This is the property that we're after. So it's actually a consequence of the one right before it, and the fact that you can calculate the area of m. You can calculate the integral of m dx, little or small, because hey, it's just a rectangle, so we can calculate the area of rectangles, you know. So that's not bad. One moment, I must look in my notes, see where we are. So we're roughly speaking page 212 or so, but not exactly. All right, there's two other properties of integrals that are important. One of the properties is that if we have the integral from a to b of f of x plus g of x, it's equal to the integral from a to b of f of x dx plus the integral from a to b of g of x dx. And also, if we have the integral from a to b of a constant times f of x, well, guess what? You can pull the constant out. So the definite integral, much like the indefinite integral, also has these two properties which I refer to collectively as linearity. It breaks over sums, and we can pull constants out. All right. Oh, there's one other thing I neglected to define. Also, I keep forgetting. This is part of my definition of the Riemann integral, if you look in the notes. I forgot today in class. What do you think the integral from a to a of f of x dx should be defined to be? So this stuff up here, this is all still part of the definition of Riemann integral at the top of the board. And if you want where that is in the notes, it's on page 210. This is definition 6.2.21. What do you think the integral from a to a of f of x dx should be? 0. Very good. Yeah. Correct. I guess there's one other thing I've neglected here. It's kind of a consequence of everything I have on the board, but it's this. If 0 is less than or equal to f of x, then the integral from a to b of, then 0 is less than or equal to the integral from a to b of f of x dx. I think I said that, but I haven't quite written it. But the integral of a non-negative function is a non-negative number. All right. Now I have a proof. I have a proof in the notes of this thing I wrote here that you can break the integral up into pieces. And I actually go through the mechanics of taking a partition from a to b and breaking it into a partition from a to c and another partition from c to b and chasing the limits down. And don't bother reading that proof. Like the reason it's there is just to illustrate how hard it is to prove it directly from the definition of Riemann integral. It's so much easier to just give plausibility arguments from pictures. As a point of personal history, it took me a whole faculty meeting to come up with that proof, like a 3-hour, one of these things where you listen to external talkers, speakers come in and tell you about generation Z and about, or maybe it was generation X at the time, I forget. They're always talking about the next generation and about, how you can think of everybody in the same terms, which I just reject categorically. I don't want to think about people in terms of their generation. I want to think about people as individuals, But anyway. It took me a long meeting to come up with that proof, though, I'll tell you that. Okay, so those are the properties of the definite integral. And these properties will all have they'll mean things for the area function I'm about to define. Okay, so what's an area function? It's a function which calculates the area, right? I mean, that wouldn't be wrong, but I mean something specific about this. So what we're going to do is we're going to talk about the area relative to like a starting point. So let's talk about this here, area function. So calculate area under y equals f of x from a to x. So we'll call this a of x for a for area. And if you think about it, that's just going to be the integral from a to x, all right? But the trouble is, I'm thinking of x as a specific, value, right? So I shouldn't use that same x for the integration. So I change the letters here, and I say, well, like f of t dt, right? So, I mean, I kind of want to write f of x dx there because that's what we've been doing, but I shouldn't do that because x is the specific point we're calculating the area to. Like here's a picture, a, x, where maybe the function looks like this, I don't know. So we're calculating the signed area from A all the way to x, right, actually. So to be honest, I should really say signed area. Truth be told, right? So we're using a variable bound, right? A variable bound to set up this. Now, do you agree that this should calculate the area? Does that make sense to you, that it's reasonable to suppose that would calculate the area of that region? Signed area. So here's the annoying thing, is if I still want to call this the y and the x-axis, well then I'm thinking of x as something fixed here, but also as the variable. There's a danger for confusion there, but anyway. So we write t over here to make sure we don't make that confusion. Now, the question is, what can we say about these area functions? So the first thing I do in my notes is just to calculate the area functions in some simple cases and see if we can say anything about the area function. So we kind of already did this today, but example 1, what if we had f of x just equal to like a constant, So if we're starting at A, and we're going over here to x, right? We'll think of x being greater than a just to keep things simple. What's the area under the y equals constant graph from a to x? You can tell me, right? A, in this case, a of x is what a of x is equal to? Okay, so the integral from a to x of c dt. I mean, from direct geometric reasoning, it's what? It's the constant times x minus a, isn't it? Do you guys see that? If no, just tell me no, okay? Now, there's not many things we can calculate the area of easily, right? But another thing we can calculate the area is like the area under a line, right? So if we had like example 2, and I'll keep it relatively simple, I'll look at f of x equal to x. That way we can look at the graph, So that's this guy, right? And let's look at the area under that line y equals x, say from A to x. So can you guys tell me what the formula is for that? How would you calculate the area of this sort of trapezoidal region there? Well, yeah, with an integral, but what's the formula for it? I mean, the thing is we don't know how to do these integrals yet, right? Well, we do, but we don't want to do it the way we did it last class, right? Because that was horrible. We certainly don't want to take these infinite limits. So here we have t dt. Remember, we don't know the fundamental theorem of calculus yet, despite the fact I told you it a couple times. I want you to learn it, but I want you to forget it for the sake of this particular talk until we find it again. So, I mean, my question is, from direct geometric, like high school or middle school, whatever, algebra reasoning, what is that area? Here's a question.
X minus a times.
What's this area? So it's a triangle, right? So the red triangle, it has A and A there, right? The base and the height, both A. So 1/2 A squared is the area of the red triangle. What's the area of the purple triangle not yet drawn? See, that's got x and x, right? So it's 1/2 x squared. The purple triangle has area 1/2 x squared. So what's the area of the trapezoidal region I graphed in green? It's the area of the big triangle minus the area of the little triangle. Do you agree? Does that make sense? So that's 1/2 x squared minus 1/2 a squared. So guys, what's going on here? Let me rewrite the last thing. See, this last one was cx minus ca. All right, so question. What's dA dx for this one? What's the derivative of the area function for this second example? If you C is a constant, A is a constant, differentiating with respect to x, this formula right here, what do you get? How about this one? Differentiate this with respect to x, what do you get?
1x.
Yeah, x, right? Here you get c, right? Notice that we had f of x equals to c for this one. We had f of x equals to x for this one. What does this mean? For both of these examples, what can we say about the area function? The area function is a function that when you differentiate it, it gives you back the function you're finding the area under. Let me put it into words. The area function integral from a to x of f of t dt is an antiderivative of f of x. That's what both of these examples illustrate. That statement is actually the fundamental theorem of calculus, part 1. FTC1 says that d dx of the integral from a to x of f of t dt is equal to f of x. This is the claim of the fundamental theorem of calculus, part 1. And it's exactly what we just saw in examples 1 and 2. I can give you another plausibility argument in terms of a picture, and I think this picture is actually very powerful. So if you have A, right, and you go to x, and then you go a little bit further to say x plus delta x, right? then you can ask, what's this little, well, I can say x plus dx, actually, for the purpose of this argument. I can ask, what's this dA? Well, dA, what's this little bit of extra? So if this is a, going from a to x, what's the extra little bit of area going from x to x plus dx? Well, what's the height here? I mean dx to be very, very small, So the height here is f of x, yeah? What's the width of this green shaded region I'm about to, this infinitesimal, yeah, and very good, x plus dx minus x, and what is that? What is x plus dx minus x? X's cancel, right? It's just be dx, yeah. So what this suggests to you? This suggests to me that dA dx is f of x. So this is a proof for a certain kind of person, maybe an engineer. But if you really, really dig into it, it's really more a misuse of notation in some sense. But anyway, this is, I find this to be very comforting that this works like this. But that's not a proof, right? It's not a proof. How would you prove the fundamental theorem of calculus part 1? That's the next thing on our plate. How are we going to do that? So the proof is from page 219 to 220. I'm going to try to go through it with you guys. This actually will take us back to the start of the course. So what we want to do is we want to calculate the derivative. So we're trying to prove the fundamental theorem of calculus part 1, right? So we're trying to calculate. So we're going to let a of x be the integral from a to x of f of t dt, okay? And so we want to calculate a of x plus h. Right? Well, a of x plus h, and so we're trying to calculate a prime, right? Our goal is to calculate a prime of x. And you remember a prime of x, what is it? Limit as h goes to 0 of a of x plus h minus a of x over h. This is not part of the proof. I'm just giving you, here's, sidebar. This is why we're doing what we're doing, because our goal is to calculate this limit, right? So to do that, we need to figure out what is x plus a of x plus h. Well, that's the integral from a to x plus h of f of t dt. All right? And that is can be broken up. That's the integral from a to x of f of t dt plus the integral from x to x plus h of f of t dt, using one of those properties of the Riemann integral we mentioned before, right? But what is that? See this? This is just the area function again, right? So solve this for the difference quotient of a of x plus h, of a of x. So we've got a of x plus h minus a of x, right? Divided by h is going to be equal to 1 over h times the integral from x to x plus h of f of t dt. Right? And that's what we want to take the limit of as h goes to 0. Right? All right, so here it gets a little technical for just a second, but not too bad. So we're assuming f is continuous, right? F is continuous on the closed interval from x to x plus h, right? Thus, there exists, like, let's say, u and v in this interval, right? Such that f of u is less than, let's see how I say it, f of x is less than or equal to f of v. Right, so I'm going to assume, I'm going to assume h is greater than 0 for the moment, for this down here. Right, if h wasn't greater than 0, that wouldn't quite make sense to write that, you know. So yowzers. What on earth did I write that? Sorry, guys. Okay, so there's a step in my notes which, I mean, I don't think it's wrong. It's just I don't see it that way today. So I see it a different way today. So I'm gonna do it the way I see it today, which is if we integrate this, use the properties, you know. The integral from x to x plus h of f of u dt is less than or equal to the integral from x to x plus h of f of t dt is less than or equal to the integral. Now, how do I know this v and this u exist? That's the extreme value theorem, right? There's a minimum and a maximum. That's the thing that underlies the closed set test, closed interval test for us. Like a continuous function has to attain a maximum and a minimum on a closed interval. So, look, this has no dependence on x, and neither does that. So, this is just like a constant. And what's the length of the integration region? It's h. So this gives us h, f of u, less than or equal to integral from x to x plus h, f of t dt, less than or equal to h, f of v. All right? Which then gives me f of u less than or equal to 1 over h, integral from x to x plus h, f of t dt, less than or equal to f of v. All right. What happens if we let h go to 0? Wouldn't exist. Well, I mean, it's if think about this. If h goes to 0, what happens to this interval as h goes to 0? It does what? It shrinks to just the set containing just x, right? So if u and v are taken from this set, as h goes to 0, u and v must both become x itself. So like u goes to x and v goes to x as, you know, x to x plus h shrinks to the set just containing x, you know? So what does that tell us? That tells us that the limit as h goes to 0 of a of x plus h minus a of x divided by h is equal to what? See, this is what that difference quotient is equal to, but we've just shown that that is what? It's, in the limit, it's larger than f of x, and it's smaller than or equal to f of x. Therefore, by the squeeze theorem, this must be equal to f of x. So, f of x by squeeze theorem. But that's exactly what we set out to prove, right? Now, to be fussy, I've only proved it for the positive h, the right limit, you know? And you can go through and make a similar argument for h being negative. All right? So there you go. That's almost the whole proof of the fundamental theorem of calculus, part 1. Sorry. Oh, now that you're here, there you go. Again, that was on like page 220 has a few more details than I've written on the board, but that's it. Now, I don't use this fundamental theorem of calculus that much. The fundamental theorem of calculus that I've used already with you guys in class that I keep talking about is FTC2. The fundamental theorem of calculus part 2 is actually the thing we tend to use in applications far more. Oh, I'll leave it, sorry. So what was FTC2? I'll write it up again. Theorem FTC2, fundamental theorem of calculus part 2. Suppose f continuous on the closed interval from a to b, and f has antiderivative f, then the integral from a to b of f of x dx is exactly f of b minus f of a. Oh, are you good on this down here now? Yeah. What's another way to look at fundamental theorem of calculus part 1? Is what it really says is that if a function is continuous, then on a closed interval, then it has an antiderivative. That's pretty neat, right? Because the opposite direction definitely isn't true, right? If a function's continuous, does it have a derivative? Well, no. We know examples that are counter to that, right? The absolute value function is continuous on the reals, but it's not differentiable at 0. But somehow, the other way around, if you have a continuous function, Well, it has an antiderivative, and that antiderivative is, you can construct it as an area function, right? Is there just one? Certainly not, right? You could choose your a to be different things. You could start the area function with a different base point. You notice that? Like, our choice of a is arbitrary here. I usually make a equals to 0 if I have my choice, you know? Okay, so FTC2, we need to prove this here, and then we'll get to examples pretty soon. So this does not take as long. If f is continuous on AB and has antiderivative f, right? What do we know? Both f and the integral from a to x of f of t dt are, and let's just call this thing a of x, right? Are antiderivatives, right? That is, f prime of x is equal to a prime of x, right? And they're both equal to f of x. But what does that mean if the derivatives of both of these functions are equal, right? That implies what? That implies that, let's see, how do I want to go with it? F of x is equal to the area function plus a constant, right? If they have matching derivatives, they must be related by just a shift of a constant, because we're talking about a connected domain here, this closed interval. Now, okay, so then what? Now, I say since f and a are differentiable on AB, that implies f and a are continuous, right? And so what I do here is I say, okay, so I'm going to look at f of a as the limit as x approaches a plus a from the right of f of x, right? That's going to be the limit as x approaches a from the right of what? Of a of x plus c, right? So what is that? That's the limit as x approaches a from the right of the integral from x to a, right? Excuse me, idiot. Me, not you. A to x of f of t dt. So what happens to that? What can you say about this limit? And plus a constant, right? That's a constant. The limit of the constant is just the constant again, right? Properties of limits, limit of the sum of the limits. But what can you tell me about this one? So here I'm using, right here I'm using the continuity, right? That the value of the function is equal to the limit of the function approaching the point. That's the continuity right there. Do you see it?
Yeah.
What is this? As x goes to a, we're getting the integral from a to a in the limit, right? Which is, as you told me earlier, 0, right? So this is 0. So it looks like f of a is just equal to c. How about f of b? Limit as x goes to b from the left, I believe, yep, of f of x. And so that's the limit as x goes to b from the left of a of x plus c, which is the limit as x goes to b from the left of the integral from a to x rather, f of t dt. And again, I'll just add the constant because it, But Well, what is this? Well, in the limit as x goes to b from the left, that just gives us the integral from a to b. Yeah? But actually, this last thing I wrote, instead of writing c there, what I'm going to do is I'm going to erase that c. And because we know what? C is equal to what? See this right here? C is f of a, right? So I can replace this with that plus f of a from the line above. And thus we have the integral from a to b of f of t dt equals f of b minus f of a. And by the way, this is same as saying the integral from a to b of f of x dx equals f of b minus f of a. Those are logically equivalent. The x and the t in both of these are called dummy variables of integration. Again, the answer for a definite integral, if it exists, and certainly we know they exist for continuous functions, the answer is a number. It doesn't have an x dependence, it doesn't have a t dependence. The x and the t, they're used up in the process of the integration, if you will. So it's very different than differentiation, where we differentiate something as a function of x, and more often than not, we get, you know, what? We get something that actually is, again, a function of x. I have one more proof of FTC2, but I'm going to save it for another day because I think I've done enough proofs for today. I want to do examples in our time now. Let me see what time it is, though. 1:30. Let's see. We started at 12:30. I think we should take a 10-minute break. Would that be good for you guys? So we'll start again at 1:40. Okay.
Maybe
You want to end early?
yeah, maybe that's better.
All right. End early is always popular, so let's end at 2. Would that be better? Okay. Well, I'll let you. You're fine. I know I write at the speed of light when I have whiteboard markers. So the thing I'm skipping over at the moment is the the intuitive constructive proof on page 222. I will come back to that. And I will also come back to what I call FTC3. That's just me. Nobody else calls it FTC3, but I'll come back to that as well another day. Oh, okay. So, all right. Let's do examples. So, example 1. Suppose you want to integrate from 0 to pi sine of x dx. So what's the antiderivative for sine? So here we have f of x is sine. So we antidifferentiate, we get the antiderivative is, what is it? Minus cosine. Very good. So we do minus cosine of x, and this is the notation we use from 0 to pi. So that notation is just like this right here above. We could rewrite also as f of x evaluated from a to b. This is the evaluation bar. It's the standard notation. Anyway, so what is that? That is minus cosine of pi minus a minus cosine of 0. What is that equal to? You guys can make me do it. Cosine of pi is -1, right? So minus a minus 1 is 1. And cosine of 0 is 1. So minus a minus, we get 1 plus 1. We get 2. So the next one, integrate sine of x from pi to 2 pi. What happens there? So this time, same antiderivative, right? Evaluate from pi to 2 pi. So I got myself a minus cosine of 2 pi plus the cosine of pi. If you don't mind, I did the minus in my head and wrote a plus. Be careful with that. It'll get you into trouble. It's a good idea to write it out. This is more often than not where people make a mistake. They think they got 2 minuses and they got 3. Certainly one of my principal vices. What does this work out to? So you got -1, -1, we got -2. Let's think about this graphically. It makes so much sense. So we've got sine, right? And here we're going 0 to pi to 2 pi, right? So what this calculation shows is that you've got area 2 here, and you've got area, signed area, -2 there, and this explicitly verifies my claim earlier, which was what? The integral from 0 to 2 pi of sine of x dx is what? 2 minus 2, right? Now, of course, you don't have to break it into pieces. You could show directly that the integral from 0 to 2 pi of sine of x is 0. Here, I'll do the same thing with cosine. Suppose you're going to integrate from, let's say, pi to 3 pi of cosine of x dx. How would that go? What's the integral of cosine? Sine, very good. So we do sine of x, evaluated from pi to 3 pi, which is what? Sine of 3 pi minus sine of pi, which is 0. Now, to understand why that happened, the mechanics of all that, well, cosine, let's see here, pi and 3 pi. I didn't do a very good job. Graphing it, right? My graph is actually quite lopsided because if I'd done it correctly, is that right? 3 pi. Pi to 3 pi. Yeah, 2 pi is in the middle. So if I'd done it correctly, you should be able to see that this area and this area together are equal in magnitude. But of course, those count as negative because they're below the x-axis to that area. And in fact, this would be area 2, and you got a -1 and a -1 over there in terms of the signed area. By the symmetry, I'm pretty sure that's what happens. Here, we could figure it out explicitly. What's the integral from pi to 3 pi over 2? Cosine of x dx. See, that should be whatever this is right here. Right? Because that's